In this video I'll be talking about step doubling. So the reason why we're going to use step doubling is it's all to do with how the accuracy of our ODE solvers. Now the accuracy of a solver is based on one of three things. It could be the order of accuracy of the computational method, so you know that first order methods are not very accurate, second order methods are more accurate, fourth order methods are more accurate still. But as we tend to increase the order of accuracy, we also increase the complexity, both in the derivation and the application of the methods. The second thing which affects the accuracy of a method is the size of the step length used. So in general, the smaller the step length, the more accurate. But the problem with using a really small step length is that it's going to use far more steps and therefore far more computational resources. And the third thing that affects the accuracy is the behaviour of the solution. So if you have a solution which has a rapid change in the value over a small period in the independent variable, so i.e. a very steep curve, you have what we call a stiff problem, and this requires very small step lengths. So these are a few things which we have to deal with or consider when dealing with ODE solvers. Now we're going to look at the accuracy of Runge-Kutta methods and going to introduce something called Big O notation. Okay, so the definition of Big O notation is you can have a function f of h, and we say that f of h is equal to Big O h to the n if the following is satisfied. So if the limit as a function divided by h to the power n as h gets small, if that limit converges to some value c, which is a positive value. So what this means is for small values of h, big O h to the n is approximately equal to some number, so this c is some number, times h to the power n. Okay, so what that means is as h tends to 0, the value of big O h to the n will tend to 0 at some rate, which we don't know what it is, but at a rate faster than the polynomial h to the n will tend to 0. So what this means is this big O h to the n it's kind of a limit. It's kind of like the worst case scenario of our method. So if n was 2, so we have what we call a second order method, okay, the actual error in our method will converge at a rate faster than h squared. It can be shown that the estimate of a local truncation error, remember the local truncation error is the error at each step of your method, and that's attributed to the truncation of the Taylor series. So the estimate of the local truncation error of the classical fourth order Runge-Kutta method is this. Okay, if see the lecture notes for where I got this from. So it's h to the power 5 divided by 2880 times the fourth derivative of y. Now the global truncation error, which is going to be denoted using big E, of the function y using some step length h, after n steps is simply the summation of the local truncation error over all the steps. So here we've got summation n equals 1 to n. What we're saying is this is going to be, this is the error, is going to be equal to big O h to the 4. So that means this is a fourth order error. Now, what happens if we halve the step length? So if we have a fourth order method and we halve the step length, so instead of h we're using h over 2, well what was going to happen is, if I just go back a slide, so we have this c times h to the power n, so we have c times h over 2 to the power 4, because that n is 4 there. Okay, so we're going to have a 16th of the error for h. So by halving the error, we reduce the global truncation error by 1/16. So you can see that as we reduce the step length h, so as we halve step length h, not half the error, as we reduce step length h, we significantly reduce the error. So that means the smaller step length you use, the more accurate. What first method which we're going to be looking at in order to try and improve on the computational efficiency and accuracy of a method is called step doubling. Now in the past, whenever we dealt with Runge-Kutta methods, we've always used a constant value of the step length at h. Well, the step doubling, what this does is it seeks to adjust the value of h depending upon how accurate the solution is. So the basic premise is adjust the step length based on the estimated accuracy of the solution. Now, for each step in the solution, we calculate two solutions. One using a single step of length h, so that would be your usual sort of application of the Runge-Kutta method, and the other we use two steps of length h over 2. So we've done 3 steps in total. So 1 using step length h and 2 using step length h over 2. Then what we do is we use these solutions to estimate the error of the 2-step solution. Okay, so it's assumed that the h over 2 should be more accurate than using step length h. So we estimate what the error is using step length h over 2. Now, if this error is less than some acceptable tolerance, so that's going to be something which is set by us or set by the user, so usually some small number, maybe 10 to the minus 6. So if the error is less than this tolerance, the 2-step solution is used. So this 2-step solution using h over 2. And then we proceed on to the next step. Furthermore, if the error is much less than the tolerance, so usually 1/10 of the tolerance, then h is doubled, because what this means is we're using too small a value of h. We could actually use a larger value with not a significant loss of accuracy. If, however, the error was more than the tolerance, what we do is we halve h. So what we do is we assume that our current value of h is too large. So we halve h and we repeat the whole step again. So diagrammatically speaking, we have a single step of length h. So here we have our solution yn, and this is the solution over 1 step of length h. And in terms of the calculation of the stage values, we need the k1, k2, k3 and k4 for our standard 4th order method. Now if we were to use a 2-step solution, so we do one step of half h and another step of half h, we need k1, k2, k3 and k4 will be our stage values, and then we have k1, k2, k3, k4. Okay, so in total we have 11 stage values. Now you may count these up and say, hang on, it should be 12, but this k1 is going to be the same for both the single step solution and the 2-step solution. So what we're going to do is we're going to examine or estimate of the error in our 2-step solution. So if we let y with a tilde on top, I don't know how else to say that, so it's just a y with a little tilde hat. Okay, this is going to be the exact solution over a single time step. So y1 is our single step solution, and so this is going to be y1 plus some error. Okay, ordinarily this would be y1 plus big OH to the p plus 1. Okay, but what I've done here is I've actually taken out one of the term from big OH to the p plus 1. Okay, so I've taken one of these out here to give us ch to the power p plus 1. If we do the same for the 2-step solution, so this is the one with h over 2. Okay, so instead of h we go over half h, but we've got 2 steps of it. So if I subtract these two, okay, and solve for c, eventually we get this down here. So y1 is our solution for 1 step, y2 is our solution for 2 steps, and p is the order of our method. Okay, and if we substitute this c back into this equation at the top, okay, we get this. So what this tells us is our exact solution is equal to our 2-step solution plus this term, which we can calculate because we know what y1, y2, p is, plus this order of error. So in essence, this means we've increased the order of accuracy of a pth order method toward a p plus 1 by using that 2-step solution with half the step length. For example, if we're using 4th order Runge-Kutta method, p would equal to 4, and our exact solution would be our 2-step solution plus y1 minus y2, so that's a single step minus the 2-step solution. Take the absolute value of that, divide by 15. Okay, so this term in the middle okay, gives us an estimate for the error of the two-step solution. Okay, so this is what you have down here. So this is what we use to check against our tolerance. So here's the algorithm. Okay, so this is a step doubling method for solving an initial value problem. So if you're presented with an initial value problem, you have some value solution of y at the start of t. Okay, so you initialize t0 to be t start. You initialize your initial conditions to be the initial values. Set a counter n, so this is going to be your loop counter, and you define your Runge-Kutta parameters a, b, and c. Now we're using a while loop here because when you change the step length, you do not know ahead of time how many steps you'll need. So we can't use a for loop, so we have to use a while loop. So this while loop loops until t, or while t is less than our t end. So that's that t end up here. First thing we do is we just do a check to see will our value of h take us beyond t end. Okay, so h is the minimum of our current h or t end minus t. Okay, so that just ensures that h does not overshoot t end. Then you apply two-step solution. So you calculate your Runge-Kutta method twice. Okay, and then you also calculate your Runge-Kutta method once. So twice using h over 2, once using the step length of h. Then you calculate this estimate. So for example, if we were using the fourth order Runge-Kutta method, this would be over 15. So your single step solution minus your double step solution. If the estimated error is greater than tolerance, then the solution does not satisfy accuracy requirements. So what we do is we halve our h and then start again. So if you notice here this if statement, okay, this terminates down here. So we don't proceed to the next step. We halve h and then we do this whole thing again. If, however, est was less than tol, that means the solution satisfies the accuracy requirements. So we update t, we update our solution y to be the two-step solution, and we increment our counter. So n is some counter, so we increment it by 1. Furthermore, if our estimated error is much less than tol, usually about 1/10, okay, what we can do is we can double the step length h. So if we got a solution which is well exceeds the accuracy tolerance, we can actually risk increasing our step length there.